Hi everyone, in this video we will discuss experiment 8 of Power System Simulation Lab. The objective of this particular experiment is to replace generator connected to bus number 2 of IEEE-9 bus system by wind turbine generator, type 4 wind turbine generator. So we have already simulated the 9 bus system using DSA tools as experiment in the experiment number 7. uh, so in that case we modeled all the generators as synchronous generators only. Now in this particular case, generator 2 connected to the system will be type 4 wind turbine generator. Now why we need to study this renewable integration? Because this renewables, let's say commonly used renewables are solar and wind. So these two, if we are connecting to the system, first we will discuss about solar. Solar does not have any rotational mass. So if a solar is connected to the system, it cannot provide any inertial response to the system, unlike the synchronous generators. So synchronous generators will have rotating mass. Let's say the turbine is there. The turbine will be rotating, so some kind of kinetic energy will be stored in that turbine, and if there is any contingency happening in the system, so this power can be transferred to mitigate or to control the frequency deviation within the limit. So this energy transfer cannot be is not possible with the solar or solar. Then about wind turbine generator, uh, wind turbine does have a rotating mass, but these wind turbine generators are connected to the system through power converters. So again, we want that inertial, even though we can have kinetic energy in the rotating mass, we cannot transfer that energy to the grid at whenever it is necessary. So um, again we won't be having any inertial response. Now that's why we are trying to see how the system will get affected by renewable source integration. Let us move on to type 4 wind turbine generator. Okay, so basically there are four types of wind turbine generators. The why we choose type 4? Because the model of type 4 wind turbine generator and PV model are comparable. uh, because type 4 wind turbine generator has two converter levels, and so it is totally isolated. The generator is totally isolated from the grid. The inertial response provided by this particular model is zero to the system. That's why we are choosing type 4 wind turbine generator. The model WECC model of type 4 wind turbine generator consists of four components: plan level controller, then there is a power controller, then drivetrain model is there, then generator converter model is there. So uh, this plan level controller is can be omitted if like it's not a compulsory component in this modeling. So in this particular experiment we will be modeling the rest three components. Drivetrain model is used for emulating the oscillatory modes, and then we have a PQ control and current limit control basically. Uh, then we have a converter model, uh, and so it's like we the models present in model name is like the drivetrain model is WTGTA, and controller is REECA, and converter is REGCA. These are the models which we are going to use. So let us start. uh, so first of all we have to open the already simulated 9 bus system in DSA. We'll start from PSAT, uh, and we have to open the generator. So we are going to replace second I mean the generator connected to bus number 2 by wind turbine generator. So double click there and you can see wind machine option here. So as of now the MVR control mode is selected as not applicable. Now we have to select, there are three different options available. So it's like fixed power mode, then megawatt and power factor mode, like that. So we can, as of now we will go for fixed MVR control mode, and then you have to uh, give the power factor. So let's say I'll fix that as 1 as of now. Rest of the things remain same in PSCAD. So we have to click OK here. Now go to solution and solve. The solution is converging, uh, and we can save this file, save power flow, and save project. Now whatever changes required in the PSAT is done. We will open TSAT. uh, so this is the 9 bus system tsat file which we already had created. The power flow we will again just verify. So this file itself we edited. Now we will see or verify whether the same file is included here. So here bus number 2, it is now renewable source. Click OK. Then now we will go to dynamic data. Here earlier we had all the machines as synchronous machine. So we will remove this generators, exciter, and all the other components connected to bus number 2. So this we will delete. Exciter connected to bus number 2 we will delete. Then governor connected to bus number 2, delete. We have one more, power system stabilizer is also there. Now we will save this file. So now we can see like only generator 1 and generator 3 have the dynamic model. Now for generator 2 we will create a separate file, or else you can create do the modeling in the same file itself. I'm just creating one another file. uh, we can start from the drivetrain model. So as I said, the model name is WTGTA, and so we have to select the bus as bus number 2. Then P base for generator is 163, inertia is 2, then HT fraction 0.01, Then the damping coefficient is 1.5. Then 160 point K is 160.01, and P minimum is 0.0316. uh, W P minimum 0.8341. P1 is 0.4756. W1 is 0.9428. P2 is 0.5268. W2 0.9698. Then PWP 100 is 0.5273. Then WP 100 is 0.97. Model status should be in. Click OK. Now next we have the generator, or generator model is REGCA. So here bus number 2 MVA is 310. Then LVLP. So the parameters are all parameters will have is having a particular range, which uh, like based on the model. And there are two types of models. One is generic model, and the other one is vendor specific model. So vendor specific model means we will be having the model based on the requirements of the customer. Now for all the studies we will be using generic models, where we have fixed parameters. 0.9, 1.22, to, to TG 0.05, 0.02. Reactive current maximum is 999, and minimum is negative of 99. X is 0. W nominal is 0.97. V voltage upper level is 1.1, and voltage dip is 0.9. Then rest of the parameters are 0. Now the next one is the controller, REECA. So again MVA is 310, maximum P 1.12, minimum P 0.04, Q max is 0.4930, Q min is minus of 0.4930, V max is 1.1, V minimum is 0.9, dp max 99, dp min is minus of 99, iq 1.05, equal 1 minus of 1.05, I max is 1.5, kvi 60, kvp 1, kqi is 0.41, kqp is 0, kqv is 0, dbt 0.05, 0.15, 0, d filter is 0, v reference is 0, v reference 1 is 0, then p flag is 0, q flag is 0, q flag is 1, then v flag is 1, pf flag is 0, uh, pq flag is 0, vq1 0, iq1 1, vq2 is 0.5, iq2 is 1, vq3 is 0.8, iq3 is 1, vq4 is 1, iq4 is 1, vp1 is 0, ip1 is 0, vp2 is 0.5, then ip2 is 1, vp3 is 0.9, ip3 is 1, then vp4 is 1 and ip4 is 1. Model should be in. So if you want to see the block diagram of the models, you can go to help file, and there is model manual. So there we will get the block diagram. I'll save this file as IEEE-9 bus system uh, res. Now both the dynamic files should be there in the tsat file. Click OK. We will run the simulation again. So we are not changing the contingency. We are using the same generator tripping contingency. So a generator at bus number 3 will be tripping after 5 seconds. Now click on base case analysis solution. So you can see the system is now insecure. If you remember, in experiments number 7, we had the system to be in the secure zone even after a generation 3 or generator 3 tripping contingency. So we will go to the result and see how the generator speed is. So generator 3 is tripped, generator 2 id2 sorry, id1 you can see that frequency is 50, like it won't be the synchronous frequency as it is a renewable source. Now the power flow is like this: generator 3 tripped, that load is taken care of by generator 1, like that. Now we will go to SAT simulation. Here we have to use the new PFB file. So we will just confirm the generator. See, yeah, this is the exact file which we have to include here. Now the dynamic file. Here we already have the 9 bus system dynamic model, but we have edited this one, and we have to add the RES model also. So click OK, run the simulation now. So the change here, it will be the damping. One thing is that as we don't have any synchronous generator at bus number 2, it won't be participating in a but in any modes, and it won't have it won't be having any contribution. And the second thing is the frequency and damping of that system, sorry, that mode will change uh, depending upon which generator we have replaced. uh, Thank you for watching.